Hi, welcome back to a new video from Reading Research Papers series. Today we'll be picking up Flamingo paper. So I have the copy of paper printed here. Flamingo, this paper is available on arXiv. I will show you the link. But this paper was published by Google DeepMind and it's very, very popular. It's presenting a vision language model with few shot learning capability. We will briefly discuss what is a vision language model, what exactly is few shot learning, etc. There are large number of authors here. If you see this section of the paper, these are all author names. There are so many authors in this paper, and the length of the paper, counting the main section plus appendix, it's 54 pages. So to not prolong the video so much, I will not be going through the appendix part that much. I'll go through the main paper and I'll go through some of the figures in the appendix that are relevant for your understanding of the Flamingo model. We will also discuss why this model was named as Flamingo, what is so special about this model, how popular is this in the context of multimodal LLMs, etc. So with that, let's get into the paper dissection. I'm hoping to do this dissection in just one sitting of, I don't know, 1.5 to 2 hours or something like that. And after I trim some of the parts of the video, hopefully this won't be too long of a video, but I also don't know, right? I'm also recording while reading the paper for the first time, although I have read the paper a couple of times before. And implementation of Flamingo model is also not that straightforward. It's a little bit bigger model to train from scratch, and the weights of Flamingo trained model is not available in public. However, there is a model called Open Flamingo, which was introduced as almost exact replica of the DeepMind's Flamingo model, but in an open source manner. We'll also go through that GitHub repo really quickly. We will not be going through the code, but we'll just be opening the repo and seeing what they have done. If we were to run inference, what exactly can we do, etc. So with that, let's get into the video. So here on my whiteboard, I have pasted the individual pages of the paper separately, so we can start now. So you can just Google Flamingo paper. It will show up. It has around 6,700 citations. You can see that here. And paper is available on arXiv for free. So you can simply go ahead and download. If you want to print it and read through a printed version of the paper by annotating certain things, feel free to do that. So that will be a good exercise for you. But the title of the paper is Flamingo, a vision language model for few shot learning. Vision language model, or VLM, is a multimodal large language model. So it can not just have text capability, it can also process images, right? So we will see that there will be an image encoder and also an encoder which can handle text. So there are large number of authors in the paper. So I won't be attempting to, pronounce their names or mention their names because there are so many people who contributed to this paper, but we'll go ahead and read the abstract, and the paper is from Google DeepMind. So abstract: building models that can be rapidly adapted to novel tasks using only a handful of annotated examples is an open challenge for multimodal machine learning research. So usually we know that if it's a classification task or any sort of deep learning related task, you need a lot of examples for supervised learning. If it's a classification task, even for binary classification, a lot of examples are typically provided. So this is a challenge because in multimodality, if you need annotated images, annotated text, etc., or some kind of data set where there is a input label pair, it's very difficult to get in multimodal models. So we introduce Flamingo, a family of VLMs with this ability. When you say this ability here, this refers to ability to learn just from a few annotated examples. Let me just change the size of my marker. So by only providing a handful of examples which are annotated, can we have a vision language model with a lot of capabilities? So this paper introduces a few different innovations, in specifically 3 innovations which are mentioned in the abstract itself, but which are expanded in the main paper. So first is you utilize an already existing large language model and already existing image model. So there are already a lot of pre-trained vision models and pre-trained language models. So why can't we use the capabilities of those and somehow bridge it, right? So that is the first innovation: bridge powerful pre-trained vision only and language only models. So this is the first thing. Second innovation is handle sequences of arbitrarily interleaved visual and textual data. What this means is you might have seen certain documents where you have some text followed by some image, then again there is text followed by image. If you are writing a document in in Google Doc or Microsoft Word, you can actually copy paste images within the text. It can form part of the text, right? So that is called interleaved visual and textual data. So if you have a sequence where a sequence consists of words, then maybe some image, then again words followed by some image, something like that. If there are sequences of arbitrary length or arbitrary order in which you have text and image embedded, this model is able to handle that. Then seamlessly ingest images or videos as input. So not just images, it should be, this Flamingo model is also able to take images as the input. So we will see how the model is constructed and how it has these capabilities. One question you may have is, this Flamingo is actually the name of this bird. So this is Flamingo actually, this bird. So I had a doubt when I was reading the paper first, why is the model named Flamingo? You will see that soon. And of course, we'll be using ChatGPT as much as we need to answer our questions and to make this process of reading the paper much more seamless. So there is no, if you are reading a paper, you must be comfortable using ChatGPT, or even if you are taking a lecture, if there is a doubt, you have one of the most powerful, intelligent tools with you. So why not use it, right? So we'll be using ChatGPT to answer some of our questions while we read the paper. Flamingo models can be trained on large-scale multimodal web corpora. So this data set will consist of text and image. This multimodal web corpora, we'll see what that data set looks like, containing arbitrarily interleaved text and images, which is key to endow them with in-context few-shot learning capabilities. So now there is a question, what exactly is few-shot learning, right? Let's ask ChatGPT what is few-shot learning. But in short, typically few-shot learning is, with a few examples given, the model should be able to make a prediction. So in figure 1 of the paper itself, there is a very nice example given. Actually, it's over here. There is a very nice example given here. This is a chinchilla. They are mainly found in Chile. So this image is given, then this text is given, then this image is given, this text is given. This is a Shiba. They are very popular in Japan. And then an actual image of Flamingo is given, then the text is this is. Then the model should produce text as the output. So please note one thing Flamingo model does is it does not produce image output. It's a generative model which can generate text as the output, but the input can contain images as well as text. So it is a multimodal LLM, not from the output perspective, from input perspective. It can input, process multimodal, multiple modalities, but output is just text. So you might remember clip model. Clip model is using contrastive learning. You could train a vision language model to understand images as well as text. But in clip model, all that we were trying to do was, let's say there is an image of a cat and a text that writes cat. Both of these things can be represented using vectors. And in vision language model, the way in which image and text is aligned is by ensuring that these vectors which represent same idea. So if it's an idea of image of a cat or text that writes cat, those two vectors should have very high cosine similarity. So the angle between those two vectors should be very small. So if that can be maintained, so if this angle can be very small, it means you have vision language alignment. But one problem with clip model was that you could not, generate anything. You could only create alignment between vectors. You could not produce an output as a result, a new output. It could say, if you give an image from the captions that this model was trained on, which caption might be the best fit for the image. Or vice versa, if you give a caption, which image might be the best fit for this caption. That the model can do, but it could not generate anything, but Flamingo model can generate. So that is one great thing about this model. But let's ask ChatGPT what it can say about, few shot learning. What is few short learning, explain in 2 sentences, 2 to 3 sentences. I don't need a long reply, and I don't need thinking. I just need instant model. ML approach, where model learns to perform a task using very small labeled examples, often 1 to 10 examples per class. Instead of learning from scratch, the model relies on prior knowledge learned during pre-training and quickly adapts to new tasks with minimal data, right? So the term few shot learning is almost self-explanatory. All right, so now let's continue with the remaining portion of the abstract. We perform a thorough evaluation of our models, exploring and measuring their ability to rapidly adapt to a variety of image and video tasks. These include open-ended tasks such as VQA. VQA is visual question answering, where the model is prompted with a question which it has to answer. So if there is an image given and a question associated with the image, which is also given in this figure example, where is that? So this one is like that, right? This is asking, here is the image, what is this? But for the model to be able to predict, it's given a couple of examples here. So this is called few shot learning. Here model is given only 2 examples. Here is another one. So here model is given an example. If the proper example was not given, model might not realize that it has to do a mathematical calculation. It might just say, what is this? So if the model was answering, what is this? This is a flamingo. This is some city painting. This is some board. This is some mathematical operation, right? But that is not what the model is supposed to output in every single example. So here in this example, we are explicitly telling the model, for this image, what the model is supposed to do is do 2 plus 1 equal to 3. Here, the model is supposed to do 5 plus 6 equal to 11. Similarly, here, the output should be 3 multiplied by 6 equal to 18, and the model will output that. So just see the nature of the output. It's not just describing what the image is. Sometimes you want to describe the image. Sometimes you want to use the information from the image to calculate something else, right? Here, just see this. So here, the board output is underground. Here, the board output congress. So here, the output is, what is this? Sol ohms. So these are examples of different examples of few shot learning. So the model in general understands text and understands image, but depending on whether the task is visual question answering or some, mathematical calculation to be done based on some input or something else, model can do that. Or classification, if model has to classify an image into cats versus dogs. If we give a couple of examples, it can do that. So VQA, where model is prompted with a question which it has to answer. Captioning tasks. So you give an image and ask the model to put caption, which evaluate the ability to describe a scene or an event. And close-ended tasks such as multiple choice VQA. Multiple choice VQA is almost like multi-class classification. You have visual from a given set of questions. It has to answer one thing. For tasks lying anywhere on this spectrum, what is the spectrum here? Spectrum of tasks including VQA, visual question answering, or captioning, or multiple choice VQA. For all tasks ranging in this spectrum, a single Flamingo model can achieve new state-of-the-art with few shot learning simply by prompting the model with task-specific examples. We just saw that. On numerous benchmarks, Flamingo outperforms models fine-tuned on thousands of times more task-specific data, which is amazing, right? Because Flamingo is not a general-purpose model, but it can be, with few shot learning ability, it can be tuned to perform good in almost any kind of tasks in the spectrum of these 3 tasks. And this paper was accepted to NeurIPS 2022, which is a very, very big deal. All right, so now let's move on to the next page. Abstract is done. So next page is basically this full figure. We can just walk through the examples. So here the example is animals. What are these animals? Through 2 examples. Here, look at this. What is the title of this painting? Answer: the hallucinogenic toreador. What is this painting? Where is this painting displayed? Answer: Louvre Museum, Paris. Then another painting is given. What's the name of the city where this was painted? And then answer is Arles. I am not familiar with this painting, but in any case, the model is given some examples, and based on the example, model learns what to focus on when a new question is asked, and then it can answer. Then Let's take another one. Yeah. So here the model is given an image in which there are 3 pandas, right? And then expected output in this example is pandas 3. Another example that the model is provided is this image, dogs 2. And here model is just provided an image. But you know, there are like what, 4 giraffes, right? So giraffes 4 is the output that model gives. So this whole thing is the input, okay? Just please understand, this whole thing is the input. And within this whole input, the model is given two examples. With 2 examples for a new unseen data point, model can make a prediction. And here is another example where the model can take video frames as the input. So this is actually different frames of a video, and then model is asked based on the video what happens to the man after hitting the ball. And answer is, you can see here that the man is falling down. He falls down. It's probably difficult to analyze that from just this frame, because in this frame you don't know whether the person is falling down or whether the person is crouching or just kneeling down on the ground. Who knows? But with these entire frames, you can make out that the person is falling. Same thing the model can also understand. Then this example is that of multiple, image visual dialogue. So here an image is given. This is a picture of 2 teddy bears on moon. So this is what the model is giving as the output. What are they doing? Then they are having a conversation. What object are they using? It looks like a computer. So basically, for a given set of images or for a given image, you can have multiple sort of like Q&As possible with Flamingo model. One question is, why is this model named as Flamingo? We can just ask ChatGPT. My thinking is they don't explain it, I think, anywhere in the paper. Why is Flamingo model named? So I think this is based on that first example which you saw, chinchilla and what was that, Shiba, and third example was Flamingo. So maybe that was the reason. Flamingos are known for their ability to stand on one leg. Few short learning modalities. It balances vision and language. Okay. Okay, so flamingos have very good balance on one leg. Here, vision and language it can balance. Okay, I don't think this name has too much significance. I really don't know what exact, metaphorical reason why authors pick the name Flamingo, but whatever, I think it might be explained somewhere in the appendix. We can do a quick search. So this is the first figure in the second page. Flamingo can rapidly adapt to various image/video understanding tasks with a few shot prompting. Out of the box, Flamingo is also capable of multi-image visual dialogue. So these are some examples. More examples are available in the appendix. Then figure 2 we can read in a little bit after we read the introduction. In any case, figure 2 is showing the results from training the Flamingo on different tasks. But before going into figure 2, let's read the introduction section. Introduction. One key aspect of intelligence is the ability to quickly learn to perform a new task given. Let me just move a little bit here. Perform a new task given a short instruction. So this is a key aspect of intelligence. I agree. While initial progress has been made towards a similar capability in computer vision, the most widely used paradigm still consists of first pre-training on a large amount of supervised data before fine-tuning the model on the task of interest. So here when they say initial progress has been made towards few-shot learning in computer vision, I am not 100% sure which model they are referring to. So maybe we can ask ChatGPT. Here, which model are they referring to when they say few shot learning was attempted in computer vision? Not referring to specific model, but these are some models. All right. Okay. They are not referring to any specific model. The most widely used paradigm still consists of first pre-training a large amount of supervised data, pre-training on a large amount of supervised data before fine-tuning the model on the task of interest. All right. Which means you have to do a lot of hard work in pre-training before fine-tuning for the specific task, which means it's a double amount of work. What if you have to fine-tune for 6 different type of tasks? You have to do fine-tuning 6 times. However, successful fine-tuning often requires many thousands of annotated data points. In addition, it often requires careful per task hyperparameter tuning. This we have discussed in many papers. Fine-tuning is actually not easy. Although the amount of changes happening to the model is less in fine-tuning compared to pre-training, it's still expensive. It's resource intensive. Recently, multimodal VLMs trained with contrastive objective. So here they will be referring to clip paper primarily. We can check 50th and 85th. One of these must be the clip paper. Have enabled zero-shot adaptation to novel tasks without the need for fine-tuning. However, because these models simply provide a similarity score, so this is what I was explaining earlier. It simply provides a cosine similarity score between text and image. All right. They can only address limited use cases such as classification, where a finite set of outcomes is provided. So classification or image captioning, where caption is not generated, caption is picked from existing set of captions, or image identification for a given caption, basically image searching to find the right kind of image for your search query. It's basically considering query as a caption and then finding the image that best fits the caption from your dataset. They crucially lack the ability to generate language. So the models like Clip, they cannot generate language, which makes them less suitable for to more open-ended tasks such as captioning or VQA. So because captioning has to be truly generative. If an image is shown, you are generating a new caption. It should not be like, because you have 400 million examples in your training data, you can pick one of the captions from your training data and say that, hey, that caption is the best fit for your current image. That is what Clip model does, but that's not the best thing, right? It's not generating caption. Others have explored visually conditioned language generation, but have not yet shown good performance in low data regimes. So that is what this paper is showing. It will show what this visual conditioning of language means. We will see that when we proceed in the rest of the paper. We introduced Flamingo, a VLM that sets a new state of the art in few-shot learning on a wide range of open-ended vision and language tasks simply by being prompted with a few input or output examples. So you already saw this in figure 1. Of the 16 tasks we consider, Flamingo also surpasses the fine-tuned state of the art on 6 tasks, despite using orders of magnitude less task-specific training data. So this is where figure 2 comes into picture. We will look at figure 2 in a moment. To achieve this, Flamingo takes inspiration from recent work on LLMs, which are good few-shot learners, because you might have seen LLM, which is like ChatGPT, for example. It is a language model trained to predict the next word, but it can do a lot of things. It can do mathematics. It can do translation. It can write poems. It can, analyze a research paper. If you copy paste it, a lot of things it can do. And all of those properties you can bring out those properties with zero shot, meaning you don't even have to give an example. You just need to ask it what to do, or few shot. In some cases, if you want to give an example of what the model is supposed to do, you can give 1 or 2 examples in the prompt and the model can do it directly, right? So this is why it's a good few shot learner. LLM, large language models, are in general good few shot learners, meaning it does not need large number of annotated examples for it to perform really good in new tasks. A single large language model can achieve strong performance on many tasks using only its text interface. A few examples of a task are provided to the model as a prompt along with query input, and the model generates a continuation to produce a predicted output for that query. So corresponding to query, output is produced, but along with the query in the prompt, you are giving some examples. We show that the same can be done for image and video understanding tasks such as classification, captioning, or question answering. These can be cast as text prediction problems with visual input conditioning. So what is classification task? Classification task is essentially you give an image and say, hey, can you classify this into category cat or dog? So you provide the image and you provide a text sentence, and then it has to produce a sentence output. Captioning is what? Captioning is you provide an image and you say, hey, can you write a good caption for this image? And then it has to produce a text output. In visual question answering, you provide an image and then you ask a question. In this image, how many animals can you count? And then it has to produce a text output. So in all these cases, you have visual input conditioning. Input contains text and image, and output is basically a text. The difference from a language model is that the model must be able to ingest multimodal prompt containing images and/or videos interleaved with text. So in vision language model, or if we are building Flamingo, it should be able to take text as well as image. Flamingo models have this capability. They are visually conditioned auto-regressive text generation models. What is auto-regressive text generation model? See, GPT is an auto-regressive model. Whatever output it produces as the next token, it adds to the existing set of tokens, and then the next word is predicted. So ith word is predicted, then that is added to the existing set of tokens. Then I plus 1th is predicted, then that is added to the existing set of tokens. Like that, it is auto-regressive, meaning its own output is used to produce its next output. So here, this Flamingo model is also visually conditioned auto-regressive text generation model. It is a text generation model, not an image generation model, but its input can have image also. So it's a visually conditioned auto-regressive text generation model. Why auto-regressive? Because the text it produces is added into its input to produce the next token, and then it's repeated to produce the next token. It's able to ingest a sequence of text tokens interleaved with images or videos and produce text as output. Flamingo models leverage two complementary pre-trained and frozen models. So this is the most important thing you should know. Flamingo does not train its vision encoder or language encoder completely from scratch. It uses pre-trained models. A vision model which can perceive visual scenes, and a large language model which can perform a basic form of reasoning. Novel architecture components are added in between these models, in between these two models, to connect them in a way that preserves the knowledge they have accumulated during computationally intensive pre-training. So pre-training of language model or vision model is very expensive. So whatever the model has learned during pre-training should somehow be preserved during the process of converting it into Flamingo model. So they have done a few things to make sure that that happens. Flamingo models are also able to ingest high resolution images or videos thanks to a perceiver-based architecture. So we are yet to see what is this perceiver. We'll see that in next figure, I think, that can produce a small fixed number of visual tokens per image or video, given a large and variable number of visual input features. So let's say you input a 40-second video versus a 1-second video, or video resolution is different. The input has variable size, but the immediate output, which is used for, creating, let's say, sort of cross attention between language and image, has to be of fixed length. So how does it do that? A perceiver-based architecture is used for that. We will see what it looks like. A crucial aspect for the performance of large language models is that they are trained on large amount of text data. This training provides general purpose generation capabilities that allows these language models to perform well when prompted with task-specific examples. Similarly, we can demonstrate that the way we train Flamingo is crucial for its final performance. They are trained on a carefully chosen mixture of complementary large-scale multimodal data coming only from the web. So Flamingo model is trained on complementary large-scale multimodal data. Let's not focus on the word complementary for the moment. It's large-scale, meaning a lot of data points are there for training Flamingo. But then if we are training Flamingo on such a large data set, then why do we use pre-trained model? Because pre-trained models already know a lot of things about images and a lot of things about text. And whatever changes we are making to the pre-trained vision and pre-trained language so that it can take both image and text as the input, that is Flamingo model. And then additionally, Flamingo model is again trained on multimodal data, because originally vision model is only trained on vision, language model is only trained on language. No multimodality is there. So once Flamingo architecture is constructed, although these individual models are pre-trained, the whole thing has to be once more trained on multimodal data. And this data is coming from web without using any data annotated for machine learning purpose. So there is no human annotation of data in this at all. After this training, a Flamingo model can be directly adapted to vision tasks via simple few shot learning without any task specific fine tuning. This is what it is, what is amazing about the model. So although the paper has not referred to figure 3 yet, I think we can quickly go through the architecture of figure 3. Then when they describe the figure, we will understand it better. Then once more, we can come back to figure 3. So let's just focus on figure 3 for a moment. So this is Flamingo architecture. So let's start from this gray rectangle. So this gray rectangle is the input. In the input, first there is an image, then there is text, then there is image, then there is text. So there is a dog, the image of a dog, and then the text is, this is a very cute dog. Then the image is, this is. So here, can you try to predict what the output might be? Like just you as a human, what would you say? Here, this is not just saying this is a dog. It says this is a very cute dog. So there is an adjective associated with dog, right? So based on that logic, if you are a human and if you are, extending this, you will say something like, this is a very angry cat or something, because the cat's face look a bit angry, right? So the output this model is expected to produce, because please remember, Flamingo model only produces text output. It does not produce image. So the output you are expecting from this is something like, this is an angry cat. So now let's see what happens. So first, this whole thing has to be converted into text only part and image only part, because image encoder can only take image. Text encoder can only take text. So before passing this into text encoder, what is done is wherever there is image, an image token, something that looks like this, is added. Okay. Remaining is text, so text is preserved as such. So after processing this interleaved visual text data, the processed text will look something like this. So whenever there is an image, it's replaced with an image tag. So image, this is a very cute dog. Image, this is. So here in this text, there is no information about the image. I mean, this image tag is common irrespective of what the image is. So this image tag and this image tag are not different. They are the same thing. And then this processed text is passed into a language model. So this is language model with some modifications. So I will talk about the modifications in a moment. Then what happens to this image? These images are passed. There are two images, so it's passed into vision encoder. So the dog image goes through a vision encoder, cat image goes through vision encoder. It's the same vision encoder, and vision encoder will encode it into certain token length, taking in all the context. So this vision encoder is a vision transformer model, which the paper is yet to explain, but we are still going through the figure. And then this perceiver resampler has a very specific task of, irrespective of the size of the input, this perceiver resampler will produce output of same length. So then now whatever is coming here are context vectors associated with image. Whatever is coming here is context vector associated with text. Now you will see this symbol, this, ice, snow symbol. It means this is a frozen layer. This is frozen, meaning this vision transformer is frozen. So pre-trained weights are not changed, but this is a learnable layer. This is learnable. This is learnable. This is learnable, but this is frozen and this is frozen. You see this, snowflake symbol. So what they have done is they have taken a language model in which all the layers of the language model with self-attention plus multi-layer perceptron, they have retrained as such. But in addition, they have added some layers, extra layers. These are extra layers called gated cross attention. So X attention is cross attention. So cross attention dense. So we will go into the details of if we expand this layer, how does it look like? Obviously, it will have a cross attention. It will have residuals. It will have multi-layer perceptron. Here, it's almost the same. It will have, of course, self-attention. It will have multi-layer perceptron, and it will have residuals. And layer normalization will also be there in both of these. But when we draw, layer normalization is typically not drawn to keep the diagram concise. But there is an expanded version of the same diagram in the paper, which we will go through in a little bit. But basically, this is what is done. Okay. So here the tokens corresponding to image is coming. Here the tokens corresponding to text is coming. And cross attention is created between those two in every single layer. Self attention is created for the entire, corresponding to entire token sequence in this language model block. And finally, the output is a very serious cat. So see, the output is not just this is a cat. It says the output is a very serious cat. Here, in the example, if the input was like this is a dog, let's say this part was not there, very cute was not there. Here, the output will be simply this is a cat. But here, since this very cute adjective is given, the model understood that you have to also add an adjective for the cat. So it says this is a very serious cat. Very nice, right? Very good example they have selected, the authors have selected. Now let's move into contributions section. Contributions. In summary, our contributions are the following. We introduce the Flamingo family of VLMs, which can perform various multimodal tasks such as captioning, visual dialogue, or visual question answering from only a few input-output examples. Thanks to architectural innovations, the Flamingo models can efficiently accept arbitrarily interleaved visual data and text as input and generate text in an open-ended manner. So the interleaving of text and image, which is shown here, it can be in any fashion. You don't have any token constraint saying, hey, you need this many text tokens before you can have an image token. There is nothing like that. Then that is the first thing. So interleaving of textual and image data to produce textual output. So input is text and image, output is text. Then we quantitatively evaluate how Flamingo models can be adopted to various tasks via few-shot learning. We notably reserve a large set of held-out benchmarks which have not been used for validation of any design decisions or hyperparameters of the approach. We use these to estimate unbiased few-shot performance. So here they are talking about the benchmarks that they have used to evaluate the Flamingo model. Flamingo sets a new state-of-the-art in few-shot learning on a wide array of 16 multimodal language and image or video understanding tasks. On 6 out of these 16 tasks, Flamingo outperforms this fine-tuned state-of-the-art despite using only 32 task-specific examples. So in figure 1, they showed only 2 examples per task, but here to overcome the state-of-the-art before Flamingo, they used 32 examples, around 1,000 times less task-specific training data than the current state-of-the-art. So the current state-of-the-art had probably 32,000 on that order of magnitude amount of data for fine-tuning. With a larger annotation budget, Flamingo can also be effectively fine-tuned to set a new state-of-the-art on 5 additional challenging benchmark: VQA, V2, VA text, VisVis, MSR, VTT, QA, and hateful memes. So we'll see what these benchmarks are. There are many benchmarks, by the way. So figure 2, we have not gone through yet, right? It was showing this graph with the performance. Maybe we can read through this a little bit. Flamingo results overview. So this, what is this maroon color is Flamingo 80 billion model with 32 shots. And these gray color ones are previous 0 or few shot SOTA. SOTA means state of the art. These are state of the art. So here it's the performance relative to few shot. FT SOTA is what? I think I forgot what was this FT SOTA. Maybe it is few shot training state of the art. What does FT SOTA mean? Not few shot training. Yeah, of course. Yes. So fine-tuned state of the art. So FT SOTA means fine-tuned state of the art. So performance relative to fine-tuned state of the art. So fine-tuning is very expensive. So you are comparing few shot learning against fine-tuned models. In few shot learning itself, there was the previous state of the art and there is Flamingo. And here you can see that in 6 tasks. So if state of the art, if fine-tuning performance is 100% because you are normalizing the few shot performance relative to fine-tuning performance. And here you can see that in 1, 2, 3, 4, 5, 6. 6 out of these 16 tasks, performance of few shot from Flamingo is better than performance from fine-tuning. And also for all these previous state-of-the-art for few shot learning, the Flamingo model is performing better. So this relative to fine-tuning, this is only performing 41%. Flamingo is performing 66. Here it is only 15%. Flamingo is 75 and so on. So in none of these examples, no other previous state-of-the-art for few shot learning is overcoming Flamingo. And similarly, in 16 of these examples, so this is Flamingo 80 billion model with only 32 training examples, 32 few shot examples. Whereas this is fully fine-tuned. You are comparing this 32 example based fine-tuning of Flamingo with fine-tuning. So if a number is less than 100%, it means the Flamingo model with few shot is performing worse than fine tuning. If the number is greater than 100, like this 106, 109, 115, and so on, it means Flamingo model is performing better than fine tuning with just 32 examples. So here in 6 tasks, Flamingo is performing better. Okay. And here it's showing the performance of different models. So of course, Flamingo 80 billion being the biggest model, it has the best performance. So that makes sense. So let's read this. Left, our largest model, dubbed Flamingo, outperforms state-of-the-art fine-tuned model on 6 out of 16 tasks we consider with no fine-tuning. For the 9 tasks with published few-shot results, Flamingo sets new few-shot state-of-the-art. So here actually in the bar plot, there are only 15 bar plot, because in the 16th task, I think the fine-tuning state-of-the-art is not available. So our 16th benchmark, which is a rare act, is omitted because it is a 0-shot benchmark with no available fine-tuned result, which means you cannot compare it with against 100% because you don't know what the fine-tuned result for that particular task is. So that is not plotted here. But in all the tasks, Flamingo sets new state-of-the-art for few-shot learning for sure. And in 6 out of 16 tasks, or rather 6 out of 15 tasks, Flamingo sets state-of-the-art even in comparison against fine-tuning. So that is what is done here. Okay, so figure 2 is pretty straightforward. Now let's move into next section, approach. This section describes Flamingo, a VLM that accepts text interleaved with images or videos as input and outputs free-form text. The key architectural components are shown in figure 3, which I think we looked at, right? Yeah, this is figure 3. In figure 3 are chosen to leverage pre-trained vision and pre-trained language model and bridge them effectively. First, the perceiver resampler receives spatio-temporal features from vision encoder. So spatio-temporal features, why does it say temporal? Isn't image just spatial? Where is temporal coming here? Temporal is coming because if the input is a video, it will have frames. So it will have temporal information also. So spatio-temporal information coming from the vision encoder is passed into perceiver resampler. So it receives spatio-temporal features from vision encoder obtained from either an image or video and outputs a fixed number of visual tokens. So perceiver resampler, irrespective of the number of input, it outputs a fixed number of visual tokens. Second, these visual tokens are used to condition the frozen language model using freshly initialized cross-attention layers. So this is why this cross-attention is written as X-attention cross in this purple color, this gated X-attention dense. So gated, there is a tan hyperbolic gating. So I will show you why this gating is needed and what exactly it looks like. It's not complex at all. So don't worry by seeing the term. Then these new layers offer an expressive way for language model to incorporate visual information. So see here, these new layers take in information from the image. So this image information is coming into the new layer. So this new layer is which one? This purple color layer. The blue color layer is already existing layer in the language model. It's pre-trained, it's frozen. Okay. So new layer helps language model to also take image context and produce cross-attention result so that it can produce even better context vectors. So incorporate visual information for the next token prediction task. Flamingo models the likelihood of text Y conditioned on interleaved images and videos X as follows. So P of Y given X. So Y is the predicted next token, X is the input, and basically the loss is similar to cross entropy loss. Basically there are set of tokens in the dictionary and you are trying to predict which token among the dictionary is your next token. There is one token which the model is supposed to predict, because if you have an input text and if you are using the model to predict the next token, there is one token that the model is supposed to predict and there is one token that the model actually predicts. So based on actual prediction, there will be a softmax probability distribution, but there is a token that it is supposed to predict. So using the softmax probability distribution, versus the ground truth, you can construct a loss function using cross entropy loss. So where YL is the Lth language token of the input text, and Y less than L is the set of preceding tokens. X less than or equal to L is the set of images or videos preceding the token YL in the interleaved sequence, and P is parameterized by a Flamingo model. So this equation is just a mathematical representation of what we already understand from this image. So here, if it is predicting some Lth token, it has all these text tokens preceding it and these two image tokens preceding it. So these image tokens plus this token converted into this kind of a format will be used to predict the next set of tokens. And here, what are those next tokens? This one, a very serious cat. The ability to handle interleaved text and visual sequences makes it natural to use Flamingo model for in-context few-shot learning, analogous to GPT-3 with a few-shot text prompting. The model is trained on a diverse mixture of datasets as described in section 2.4. So now we can move on to the next page. The next page starts with figure 4. Although figure 4 is not yet referenced in the paper, we can read through it quickly. So figure 4 is basically the expansion of this individual layer. So this is block number 1. Then there is block number 2. Like that, there are n blocks. So nth language model block, nth gated cross attention block. So this is one such blocks. Okay. So in one such blocks, input, this X is what? Input coming from image. This Y is input coming from text. Now in the gated cross attention, there is cross attention between text input and image input and text input. Then in language model layer, which is frozen, it converts these inputs into another set of context vectors. Like this, there are n number of layers. Now this is an expansion of one such layer. So this expands to, we already know, right? In a language model transformer block, there are two things: self-attention followed by multi-layer perceptron or a feed-forward neural network. So that is this is FFW, feed-forward neural network, or MLP. And before that, there is self-attention. Similarly, in cross-attention, what will be there? There will be one multi-layer perceptron, and before that, there will be cross-attention module. So now let's see what this cross-attention means. So usually in self-attention, the queries and keys are both produced from the same sequence, right? Same sequence, a sequence is attending to itself. But in cross-attention, query will come from different sequence, and key and value will come from another set of sequence. So let's start with language model layer. So because this is something we are more familiar with, right? So whatever is coming in is converted or projected into query key value space. So this, whatever is coming in is Y. This Y is projected into query. It's projected into key and value. So key equal to value equal to function of Y. So here it does not say that key and value are the same. It just simply says same sequence is used for producing key and value. Same sequence is used for producing query. And then query key and value will be used for producing softmax of query.key transpose divided by square root of D, right? So it's basically the self-attention formula. And then there are residual or skip connections here. This is one residual connection will go around self-attention. One residual will go around feed-forward neural network. Feed-forward neural network, what does it do? It has one hidden layer which projects your, whatever is the dimensionality of your context vectors into a 4x dimensional space. So if the context vectors had 768 dimension, it will be projected into 4 multiplied by 768, that many dimensional space, and then it will project back. Now this part is simple. This, if you know the transformer architecture, this part is not at all complex. Now what about gated cross attention? In this, query is coming from language, key and value are coming from vision. And where is this vision input coming from? It's coming from the vision encoder and perceiver resampler. So from that, vision input is coming, which is projected into key and value space. And what about the input for the language? It's the sequence of language tokens where image is actually replaced by an image token, right? So this language input is projected into query. Then this vision input is projected into key and value, and then cross attention is constructed between them. Now here, there is a tan-edge gating. So what the tan-edge gating does is, look at where the tan-edge gating is getting applied. It's it's basically getting applied to the context vectors created using this language and vision output. So what this is trying to do, which we will read soon, is to make sure that the vision input is not overpowering this large language model module, because at the end of the day, this whole thing is primarily a pre-trained language model with some extra layer added in between. So this is pre-trained part with extra layer. So all these dark blue ones are pre-trained frozen layers. All these purple ones are newly added layers. So primarily this is a language model. So if too much vision input is injected into it, it may not be good. We'll read reasons why that is the case. But basically this Tannish gating will ensure, or it will give you a way to control the amount of information, vision related information flowing inside this language module. Okay. So Tannish gating followed by residual connection. So residual connection, again, there is one residual around, this one around the cross attention, one residual around the feed forward neural network. Feed forward neural network also has Tannish gating. And here cross attention, the residual around the cross attention is residual of the query itself. So query is directly passed here, meaning you can see that language input has more significance here. Why? Because here language input is directly passed here after the Tannish gating, right? If language also had to be suppressed or controlled a little bit through Tannish function, it would have passed through this. So, and also what is Tannish? Tannish will have a graph that looks like this, which has -1 to 1 as the range. So Tannish makes sure that no matter what the magnitude of the input, the magnitude of the output will be between -1 and 1. So it's a bounded function, right? Tan hyperbolic. So that is what is done here, but more details we will read in a little bit. But let's read the caption. To condition the language model on visual inputs, to condition the language model on visual input. What does this mean? This is language model, this whole thing, but we are conditioning it to visual inputs using cross attention. So for that, we insert a new cross attention layers between existing pre-trained and frozen language model layers. The keys and values in these layers are obtained from vision, while queries are obtained from language. They are followed by dense feed forward layers. So that is the reason why this is called as gated X attention dense. Why dense? Because there is dense feed forward layer, this one. Why cross attention? X attention, because there is cross attention. Why gated? Because there is Tannish gating here and here. Okay, so that's why these three terms are there. Please pardon my not so good looking drawing. These layers are gated so that language model is kept intact at initialization for improved stability and performance. So gating is so that language model can start with zero influence from images. So it can, at initialization, it almost behaves like a completely pre-trained language model, whichever model they used. All right, now let's move into vision part, visual processing and perceiver resampler, because we have not discussed about that in detail yet. Visual processing and perceiver resampler. So first is vision encoder, which takes you from pixels to feature vectors. Our vision encoder is a pre-trained and frozen normalizer free ResNet. So it's not even vision transformer, it's actually ResNet. Here I mentioned vision transformer just because it could be vision transformer, but what is actually used is ResNet. We use the F6 model. We pre-trained the vision encoder using a contrastive learning objective on our data sets of image text pairs using two-term contrastive loss from Radford et al. So this Radford et al. Is, I think, the clip paper. So two-term means you have a loss which is from image to caption, another loss term which is from caption to image. So two-term and those two losses are combined. I don't want to go into the details of that. That is why I'm just explaining it very quickly. But just two-term contrastive loss means if you have bunch of tokens, a bunch of captions and bunch of images corresponding to captions, for every image, there are n possible captions, out of which only one is correct. So you can construct a loss like that. Similarly, for every image, out of the n captions, or vice versa, I don't know which one did I say first. For every caption, there are n possible images. For every image, there are n possible captions. Only one of them is correct. So you can construct loss for every single image, considering all the n possible captions are available and you can construct a loss function. Similarly, for every caption, you can construct a loss function by considering all possible images. And this is two-term contrastive loss. We use the output of the final stage, a 2D spatial grid of features that is flattened to a 1D sequence. So the output of the final stage means finally what comes out of the vision encoder has to be a 1D sequence. For video inputs, frames are sampled as 1 frame per second and encoded independently to obtain a 3D spatio-temporal grid of features to which learned temporal embeddings are added. So learned temporal embeddings means if it is in frame number 1, frame number 2, frame number n+1, one embedding vector is added to those individual frames, and that embedding vector will be a learned embedding vector, which will somehow eventually will contain the information that temporally this is frame number 1, temporally this is frame number 2, etc. Features are then flattened to 1D before being fed into the perceiver resampler. More details on the contrastive model training and performance is given in Appendix. So we can look at the details of this in Appendix. So now we have to expand the perceiver resampler part figure. How does it look like in the Appendix? We can do that in a moment. Perceiver resampler from varying size large feature maps to few visual tokens. So perceiver resampler, as I mentioned, produces constant output sequence of constant size, irrespective of the input. So this module connects the vision encoder to the frozen language model as shown in figure 3. So in figure 3, you saw for cross attention, one of the input is coming from perceiver resampler, other input is coming from process text. So let's go here. It takes as input a variable number of image or video features from vision encoder and produces a fixed number of visual outputs. This reduces the computational complexity of vision text cross attention, because otherwise if it was variable output, you will have to account for, or you will have to say maximum token length or something. But here you are kind of constraining it. So this cross attention complexity is kind of contained by making sure that perceiver resampler produces a sequence of tokens of constant length. Similar to perceiver and detection transformer DETR, we learned a predefined number of latent input queries which are fed to a transformer and cross attend to visual features. So we'll see this in detection transformer. Actually, there were 100 query tokens which were used to produce 100 token outputs or 100 context vector outputs. Similar to that, here in perceiver resampler, something is being done. We'll see that when we look at the figure. We show in our ablation studies that using such a vision language resampler module outperforms a plain transformer and an MLP. We provide an illustration, more architectural details and pseudocode in Appendix A1.1. So let's just quickly look at the figure, because now it is time to have a look into the Appendix section. Yeah, so this is the figure 5, right? This is the perceiver resampler figure. The perceiver, okay, first let's look at the caption, then we can look at the figure. The perceiver resampler module maps a variable size grid of spatio-temporal visual features, output from vision encoder, to a fixed number of output tokens. So firstly, this is spatio-temporal. Why? Because this is spatial, XY spatial features. This is temporal because these are frames in a video. Then these frames, there are no 3 vision encoders here. There is only 1 vision encoder, but they have just drawn it as 3. But vision encoder will convert this into spatio-temporal sequence. Why is it called spatio-temporal sequence? This is spatial and this is temporal. So this is number 1, this is number 2, this is number 3. So if these are mapped by certain time frames, t equal to 0, t equal to 1, t equal to 2, because the input is 1 frames per second, then that time information is also added as a learnable temporal position embedding vector. So that is added to this. And then these sequence of tokens, so let's say now you have 9 plus 9 plus 9, 27 tokens. They are now flattened into a sequence of these many tokens. How do you construct a constant number of tokens as the input? If you need that, you first initialize some sort of query tokens. So here, let's say the number of query tokens are 5. Then this will be starting initialized as random or zeros, but basically at the end of the day, this will be learnable tokens. So these query tokens will perform cross attention with these input tokens, where these query tokens are projected into query. Actually, this also used for self-attention, I guess. So there is self-attention and cross-attention going on. If it is only cross-attention, then what is happening is query tokens will be projected into query, key and value, and then there will be self-attention. If it is cross-attention, query will be projected into query, then key and value will be resulting from these flattened sequences. And then you will have attention blocks here, followed by that the residual connections, and then followed by that multi-layer perceptron. And finally, what is produced at the output here is the context vectors corresponding to our query tokens. 5 query tokens are there. They are converted to 5 context vectors. And these context vectors are as the sequence of tokens that are fed into the gated cross attention in the language model block. So here I have a few questions which we can ask ChatGPT. First, my first question is, in the attention, is there only self-attention or is there self and cross-attention? That is my first question. Let me do one thing. I'll delete this, take a screenshot and put it here. Is there self and cross-attention both used here? Okay, both are used, but in a very asymmetric way. So cross attention, then self attention. So I need shorter output. Use only few sentences in your explanation. In self attention, where does QKV come from? If my understanding is correct, a self-attention will be constructed between those 27 tokens as well as query tokens. QKV all computed from the same input tokens. Is this done for the 5 query tokens as well as the 27? So 27 number and 5 number is just representative, I think. I'm not sure exactly whether 5 is the final number of, token sequence length produced by the perceiver resampler. Anyways, is this done for the 5 query tokens as well as for the 27 tokens coming from visual encoder? When I say this, I mean self-attention. So basically, I just want to know if self-attention is calculated for both set of token sequences. In perceiver resampler, self-attention happens only among the 5 learned query tokens, while the 27 visual tokens are never self-attended. Okay, good to know. They are used only as keys and values. Okay, that is good to know. So self-attention is calculated among just the query tokens. And what about cross-attention? Where does QKV come from? If my understanding is correct, Q will come from the 5 learned query tokens. Key and value should come from the those 27 visual tokens. Let's see if that is the case. Q comes from the learned latent tokens for sure. Key and value come from visual encoder tokens, typically concatenated with latent. So that latent query, key and value come from visual encoder token, typically concatenated with latents. Okay, so in cross attention, the learned latent tokens are also playing a role in producing key and value. Because here, in Flamingo's perceiver resampler, key and value are formed by concatenating visual tokens and learned latent tokens. So, and these latents contribute to key and value as well. Okay, that is good to know. So basically in perceiver resampler, this query in cross attention, in self attention, first of all, these all 5 tokens attend to each other so that context becomes better. In cross attention, query is produced using these 5 learned latent queries. Key and value are also produced using not just, this flattened set of tokens, but these flattened tokens are concatenated with these query tokens, these 5 query tokens. Let me just annotate. So these are our 5 query tokens. These 5 query tokens are concatenated to these 27 flattened tokens, and that concatenated entire sequence of tokens is now used for producing key and value. But for producing query, only this is used. So now my next question is, doesn't concatenation change the dimensionality? Right? Let's ask. Doesn't concatenation change the dimensionality of the tokens? How is it taken care of? No, concatenation is along the sequence dimension, not the feature dimension. So each token keeps the same embedding size. Okay, got it. So it's not concatenated. So if the dimensionality is 768, concatenation is not along that dimension. Concatenation is such that 27 tokens becomes 32 tokens. So it's not per token concatenation. Makes sense. I was not thinking correctly. So here 27 tokens are there of 768 dimension. Here 5 tokens are there of 768 dimension. Let's say 768 is just an example. And then these 27 and these 5 tokens are concatenated to produce 32 tokens. And those 32 tokens are now forming projected into key and value space. Similarly, these 5 tokens, which are again 768 dimensions, are projected into query space also. Some syncing error is happening. Let me just refresh. Okay, and what else? Now these queries. So how many context vectors are produced, by the way? Is it 32? Is it 27? Or is it 5? It should be 5 because number of queries and final context vectors that are produced should be the same. So total 5 context vectors are produced, and there is a residual connection going here, followed by that feed forward MLP, and then again residual, and then these 5 tokens which were initialized here are now projected. They are now converted into final context vectors. And there will be a few layers of this, I think. It's not just one layer, X number of layers. All right. So this is what perceiver resampler is. Now let's go back to the paper where we left off. So we left off somewhere here. So that is perceiver resampler. So next section is conditioning frozen language models on visual representations. So let's move on to 2.2, section 2.2. Text generation is performed by a transformer decoder conditioned on visual representations produced by perceiver resampler. We interleave pre-trained and frozen text-only language model blocks with blocks trained from scratch that cross-attend to visual output. So here, we are simply talking about the large language model block, which is a decoder-based block, because it has cross-attention between visual tokens and text tokens. It has self-attention between all the tokens that are available. And then finally, such blocks repeat n number of times and it produces text output. Interleaving new gated cross-attention dense layers with a frozen pre-trained LM. This we saw in terms of image already in figure 4. We freeze the pre-trained language model blocks and insert gated cross-attention dense blocks between the original layers, and these are trained from scratch. The gated cross-attention blocks are trained from scratch. To ensure that at initialization, the conditioned model yields the same result as the original language model, we use a Tannish gating mechanism. Because when the model is starting, it knows only what the large language model knows, and it knows only what the vision encoder knows. So ideally, this text decoder should produce output similar to what a language-only model should produce. And this is where Tannish mechanism is introduced. So this mechanism multiplies the output of a newly added layer by Tannish of alpha. So output of the gated cross-attention is multiplied by Tannish of alpha before adding it to the input representation from the residual, because residual connection is coming, and before you add something to the residual, and residual is basically queries produced using the text input. So if you go to figure 4, where is that? Yeah, here the residual is query produced using text input, this one. And before adding something to the residual, whatever output comes out of cross attention is multiplied by tan hyperbolic of alpha. Now, what is that value of alpha is what we should see. Where alpha is a layer specific learnable scalar initialized to 0. So in the beginning, basically, whatever goes as the input into the self attention frozen block will be just the language input. Text will not be going. Image will not be going. Why? Because this tan hyperbolic of 0 will be 0. So 0 multiplied by whatever comes out of this cross attention is 0. And what is going here? So 0 plus this language input. So that is what is now fed into the feed forward and self attention and feed forward, which means at the starting, the model will act just like a decoder for text based model. Image information is not coming. Image will come only when the tan h of alpha value is not equal to 0, right? So at the starting, it's initialized as 0. Thus, at initialization, the model output matches that of pre-trained language model, improving training stability and final performance. In our ablation studies, we compare the proposed gated cross-attention dense layers against recent alternatives. We don't have to look at what the recent alternatives are because that will be a huge digression, but we can proceed further and explore the effect of how frequently these additional layers are inserted to trade off between efficiency and expressivity. Appendix gives more details. Now, varying model sizes. We perform experiments across 3 models, building on 1.4 billion, 7 billion, and 70 billion chinchilla models, calling them respectively as Flamingo 3B, Flamingo 9 billion, and Flamingo 80 billion. For brevity, we refer to the last one as Flamingo throughout the paper. So this is the Flamingo mentioned in the paper. While so this one should be, we perform experiments across 3 model sizes building on 1.4 billion. So these are purely language only, I guess. Are these chinchilla models language only models? Okay, they are basically language only models. So the text part, the language decoder part that they use is pre-trained 1.4 billion, 7 billion, 70 billion chinchilla models. So how does this become 3 billion, 9 billion, and 80 billion? Because there are parameters coming from the vision encoder also. So while increasing the parameter count of frozen language model and trainable vision to text gated cross attention dense modules, we maintain a fixed size frozen vision encoder. So yeah, extra parameters are not just coming from vision encoder, by the way, it's also coming from text encoder and trainable perceiver resampler across different models. So you have trainable parameters in perceiver resampler. Actually, the parameters in the vision encoder part there is no training. It's pre-trained, so we don't have to count that in the billion, 80 billion size. In the language model also, most of the parameters which are coming from the chinchilla models are frozen, but the gated cross attention introduces new parameters, which is why it becomes 80 billion instead of 70 billion, and similarly 3 billion instead of 1.4 billion, etc. Resample across different models. So in all the model, the perceiver resampler part is trainable. It adds new trainable parameters. Multivisual input support per image or per video attention masking. The image causal modeling introduced in equation 1 is obtained by masking the full text to image cross attention matrix, limiting which visual tokens the model sees at each text token. So this sentence is not easy to understand unless you see an image. So we will look at the image in the appendix in a moment, but let's read through. At a given text token, the model attends to visual tokens of the image that appeared just before it in the interleaved sequence, rather than to all previous images. So at a given text token, the model only attends to visual tokens of the image just appeared there just before, not to all previous image. Through the though the model only directly attends to a single image at a time, the dependency on all previous images remain via self-attention in language model, because language model takes self-attention of all context vectors. So this single image cross-attention scheme importantly allows the model to seamlessly generalize to any number of visual inputs, regardless of how many are used during training. In particular, we use only up to 5 images per sequence when training on our interleaved datasets. Yet our model is able to benefit from sequences of up to 32 pairs. This is where the 32 shot, few shot training with 32 shots is mentioned, 32 pairs of images and videos and corresponding text during evaluation. So this paragraph, you will only understand 50% just by reading. For fully understanding it, you have to go to the next, the figure in the appendix section. I want to show you one specific figure. So figure number 7, okay, this is the figure now we should look at. So first, before we look at the figure, let's read the caption parallelly so that we understand it better. Figure 7, interleaved visual data and text support. So given text interleaved with images or videos, example coming from a web page, we first process the text by inserting image tag at the locations of the visual data in the text, as well as special token BOS for beginning of sequence and EOC for end of chunk. So this we can see. So if our input is something like this, cute pics of my pet, I can't zoom in this any further, but cute pics of my pets, followed by this image saying my puppy sitting in the grass, followed by this saying my cat looking very dignified. Then this will be converted to this. So since it's the sequence beginning, it starts with BOS sequence, cute pics of my pets, then end of chunk. So this chunk is ending. Then there is an image. So this image tag, followed by that, my puppy sitting in the grass, then end of chunk, then followed by that, this image, my cat looking dignified, end of chunk, right? So after this, there is one end of chunk. Then after this image and the text, there is another end of chunk. After this image and the text, there is another end of chunk. Before all of this, there is beginning of sequence, BOS. Then images are processed independently by the vision encoder and perceiver resampler. So these two images go through vision encoder. There are no two encoders. There is only one encoder, but here we are showing it just for understanding. And then perceiver resampler will convert it into a sequence of fixed number of tokens. At a given, to extract visual tokens, at a given text token, the model only cross-attends to visual tokens corresponding to last preceding image or video. 5 indicates which image/video a text token can attend, or 0 when no image or video is preceding. So for all of these tokens, which are text tokens, there is no preceding image, right? Because there is no image before this sentence. The first image is here. So before this sentence, yes, there is one image. Before this sentence, there are 2 images. So 5 indicates which image or video a text token can attend to, and 0 when nothing is preceding. So these tokens are added with a 0. Let me actually zoom in a little bit somehow. Okay, I hope you can see now better. So these, one second. This 0 means only, there is no image preceding all these tokens. And this 1 means all these tokens are attending to image number 1. And this 2 means all these tokens are attending to image number 2. Now, which one is the sequence of tokens corresponding to image number 1? This one. These are sequence of tokens corresponding to image number 1. These will be sequence of tokens corresponding to image number 2. Now, among the text, so here dark blue color means attention is not masked. Light blue means a masking is applied. So now let's look at the token sequence. So you have same token sequence attending to image tokens corresponding to image number 1 or tokens corresponding to image number 2. So if it is image number 1 or image number 2, all these text tokens do not attend to any image, which means for the sequence of tokens for image number 1, the values here are all masked, which is why it's light blue. For image number 2 also, all these text tokens, there is masking. So these text tokens do not attend to any image, whether it is image number 1 or image number 2. Now, these text tokens attend to image number 1, right? So that is why here, when image number 1 is coming as the input, these numbers are in dark blue, meaning there is cross attention between these set of image text tokens and image number 1. Similarly, these set of tokens are attending to image number 2. Why? Because for all these tokens, the preceding image is image number 2. So these tokens will attend to image number 2, but to image number 1, it will not attend. So this will be masked. Similarly, when you're considering the cross attention between the sequence of text tokens and image number 1, the image number 2 will be masked. All right. So that way, the sequence, when you are constructing cross attention, will only attend to one image at a time. It will not attend to all the preceding images. It will only attend to the just immediate previous preceding image. So in practice, this selective cross attention is achieved through masking, illustrated here with dark blue entries, which is unmasked, and light blue entries, which is masked. So dark blue is unmasked, light blue is masked. So this is basically what this paragraph that we were just reading is showing. So let's go back to our paragraph. Okay, here. Now, training on a mixture of vision and language datasets. We trained Flamingo models on a mixture of 3 kinds of datasets, all scraped from web. An interleaved image and text dataset derived from web pages, image text pairs, and video text pairs. So image text pair means image caption pair. You can imagine like that. Video text means video caption pairs. An interleaved dataset will be scraped from web pages. So M3W. Interleaved image and text dataset. The few shot capabilities of Flamingo rely on training on interleaved text and image data. For this purpose, we collect multimodal massive web, so which is MMMW, so M3W dataset. We extract both text and images from HTML of approximately 43 million web pages, determining the positions of image related to the text based on the relative positions of the text and image elements in the document object model. So DOM, document object model, will give you roughly, when you are converting web pages into sequence of interleaved text and image data, where this image should be added, because in a web page it's not a sequence, it's just it's a 2D layout, but you have to convert it into a flattened sequence. So to determine where the image should be there in the relative to the text, this DOM is used. DOM is like if you are familiar with web development, you will know. An example is then constructed by inserting image tag in the plain text at the locations of the images on the page and inserting a special end of chunk token. And this end of chunk token will be part of the vocabulary, of course, and that token will be a vector, and the values of that vector will be a learned vector prior to any image. So end of chunk is EOC token is added prior, end of chunk token is added prior to any image, which is what we saw here, because prior to image there are a bunch of text and images. Let's go here. So prior to image, EOC token is added. Prior to image, EOC token is added, because it's this EOC means this previous chunk is ending there. Okay, I also want to quickly show you a couple of images also, maybe this one, few shot interleave. Okay, prompt generation. I don't think we have reached here yet. Training dataset. Yeah, this I want to show you. Training dataset. So training dataset, this is the image text pair where there is only one image and corresponding text. So n equal to 1, t equal to 1 means image means there is no time temporal layers. The length of frames is 1. Then height, width, and number of channels. Height is, let's say, 224 by 224. Number of channels is 3. N equal to 1 means there is only one image here in this. Okay. Then if it is a video text pair, n equal to 1 because it's only one video. T greater than 1 because video will have more number of frames. 1 frame per second is taken. H and W is the resolution of the individual frames of the video. C is number of channels. If it's a color video, it will be 3. Then this is like the M3W, multimodal massive web dataset, where n is greater than 1 because there will be more than one image in the dataset. We saw, or we read a little bit a while ago, that in training, not more than 5 images were part of the training data. So you are dividing the training data such that at each point of time, the model takes in only 5 images. So n greater, but it can take more images also. So n greater than 1, depending on the number of images. So in this example that you see, n equal to 2, t equal to 1, because it's a text based, it's not a video. So number of frames is only 1, then height, width, and number of channels. So mixture of training data sets of different formats, n corresponds to number of visual inputs, meaning number of images. For paired image text data, n equal to 1. T is the number of video frames. Okay. So now let's go back. We can come back to the previous image in a little bit. We can read a little bit and come back. Then prior to an image, from each document, we sample a random subsequence of L equal to 256 tokens and take up to the first 5 images included in the sample sequence. Further images are discarded in order to save compute, because more number of images, there are more compute required for training. Then pairs of image, video, text, image or video and text. For our image and text pairs, we first leverage the Align dataset, which is again from Google, composed of 1.8 billion images paired with alt text. So alt tag, in websites, alt tag is the alternate tag associated with image. So you will see it when the image is not loading. It will show the alternate tag. To complement this dataset, we collect our own dataset of image and text pairs, targeting better quality and longer descriptions. LTIP, long text image pairs, which consist of 312 million image text pairs. We also collect a similar dataset, but with videos instead of still images. So then you will have video and corresponding alt tag or corresponding caption. VTP is video and text pairs consisting of 27 million short videos, approximately 22 seconds on an average, and they are only considering 1 frame per second. So one video, in this case, equivalent to roughly 22 images, paired with sentence descriptions. We align the syntax of paired datasets with the syntax of M3W by prepending image and appending EOC. So EOC means end of chunk to each training caption. So prepending means at the start of image caption pair, this image tag will be added just before the caption, and EOC end of chunk will be added. It's typically added just before the image, right? Or rather just after the text is over. So prepend with image following the caption, and at the end of the caption, end of chunk. Then multi-objective training and optimization strategy. We train our models by minimizing a weighted sum of per dataset expected negative log likelihood of text given the visual inputs. So we don't have to look at the equation because it's just mathematical representation of something that we already know. Then task adaptation with few shot in context learning. So before going into this section, I also want to show you the figure number 8, if I'm not wrong, in the appendix section. Yeah, this figure number 8, because figure 6 and 7 we already went through. I want to show you figure 8. So figure 8, few shot interleaved prompt generation. So here, vision to text tasks, and this is visual question answering task. So vision to text task means you just have a image in the query and you have to produce a text output based on the example. So here, this is the image, caption is a cat wearing sunglasses. This is the image, caption is elephants walking in the savannah, or explaining what is the text, what is the image. Then here there is a query, and what you are supposed to produce is something like a flamingo, expanded floater or something floating in a swimming pool or water body, something like that. Now, if it's a visual question answering, this is how it can look like. The examples can look like. Examples are image followed by what is the cat wearing sunglasses. So this is the entire text prepended by the image. So beginning of sequence, image, then question, what is the cat wearing? Answer, sunglasses, end of chunk. So this chunk is done. Then next image. So this image is this. Question, how many animals? Answer 3, end of chunk. Then next image. The question, what is on the water? Answer. So answer. So the text after this answer is what the model will produce. In this case, beginning of sequence followed by image, Then output is whatever is the caption of this image is supposed to be, a cat wearing sunglasses. Then end of chunk, then followed by next image. Output is supposed to be its caption, so elephants walking in the savannah. This is example. And then query is end of chunk, image, and then after this output text there is no more text, because now the model is supposed to produce the caption. So this is vision to text task. This is how the prompt will look like in visual question answering task. So let's read this. Given some task specific few short examples and a query for which Flamingo should make a prediction, we build the prompt by interleaving images with their corresponding texts. We introduce some formatting to do this, prepending output to the expected response for all vision to text tasks, or prompting in the format question, then followed by question, answer, followed by answer for visual question answering task. This part is straightforward. I don't think we have to spend more time. I think you understand this. Let's go back to where we left off. Section 2.5. Okay, section 2.5, task adaptation with few shot in context learning. Once Flamingo is trained, we use it to tackle a visual task by conditioning it on a multimodal interleaved prompt. We evaluate the ability of our models to rapidly adapt to new tasks using in-context learning. Analogous to GPT-3. In-context learning means we provide the context through prompt, and based on that, it can produce the output. By interleaving support example pairs in the form of image, text or video, text, followed by the query visual input to build a prompt. To build a prompt. To perform open-ended evaluations using beam search for decoding and close-ended evaluation using our model's log likelihood to score each possible answer. We explore zero-shot generalization by prompting the model with 2 text-only examples from the task with no corresponding images. Evaluation hyperparameters and additional details are given. So this, what does it mean by zero-shot generalization with 2 text-only examples? Meaning there is no image provided. Is that what it means? By prompting the model with 2 text-only examples from the task. I'm not sure what exactly this means. We'll come to that. But before that, there was one sentence that was a little bit confusing. Open-ended and close-ended. What does this mean? That also we have to ask. So let's put this into ChatGPT. Here, first question is, what does open-ended and close-ended mean? That's the first question. Second question is, what does prompting the model by 2 text-only examples? What does prompting the model by 2 text-only examples mean? Shouldn't we provide image? That's my question. Open-ended model generates free-form text answers. Example image captioning. Yeah, sure. Its answer is chosen from fixed set of options. Model scores each option using log likelihood and picks the best. Okay. So what was the sentence saying? It was saying the model can be trained for, we perform open-ended evaluation using beam search for decoding and close-ended evaluations using our model's log likelihood to score each possible answer. Okay. Beam search is within all possible tokens. The negative log likelihood is within the provided options from which the model should choose. So close-ended, the answer is chosen from fixed set of options. The model scores each option using log likelihood. Okay. Prompting with 2 text-only. So this we understand. Prompting with 2 text-only examples. This means zero-shot evaluation where the model includes 2 examples, question and answer pairs written only in text without images to describe tasks. But my question is, if we are not providing image, what is the task actually? Like, then this is just we are not using the multimodality, right? If we are not providing an image. Okay, image is still provided for query. For 2 text-only examples are used only to describe task format. Okay, what kind of answer is expected? After those, the actual query includes image and the model uses learned visual. Can you give me an example? Concrete example. Okay. What is the color of the object? Red. What is the color of the object? Blue. Okay. So the question and answer may look like this, but then the actual query will be image provided. Okay, okay, I see. So this is the reason why this is zero shot is because in the example, the image is not provided. Image is only provided in the actual query. But here we are providing the model example of how the response should look like without giving it any, here if the answer is red, we are not giving any image of a red color object. Here we are not giving the image of any blue color object, but model is understanding this is how it is supposed to predict. And then you give some, let's say, green color object or something, and you are asking what is the color of the object, and then model will say green. Okay, makes sense. And yes, this is zero shot learning. So that makes sense. We explore zero shot generalization by prompting the model with two text only examples, okay, with no corresponding images. All right. Now, these are the comparison with state of the art, which I think they had already plotted in the graph in figure 2, right? We know this, so I don't think we have to go through this table. We know in general how Flamingo performs compared to state of the art fine-tuned, as well as state of the art few shot learning examples. So this we know. Okay, now moving on to experiments. Our goal is to develop models that can rapidly adapt to diverse and challenging tasks. For this, we consider a wide array of 16 popular multimodal benchmarks in order to validate model design decisions using the course of project. 5 of these benchmarks were used as part of our development set. Coco, I don't know what is this. OK, VQA, VQA, V2. This I just know VQA. We can just quickly ask. Coco, we know common objects in context dataset. What are these? Okay, VQA is visual question answering that requires external common sense beyond the image. VQA V2, image question answer triplets. MSVDQA, visual question answering based on short clips. I need full forms. I just want to know. Common objects in context. Okay, VQA is outside knowledge. Okay, for outside knowledge. VQA V2, we understand. MS, okay, Microsoft video description. All right. VA text is video and text. Okay. Got it. Performance estimates the development benchmark may be, okay, performance estimates on the benchmarks may be biased as a result of model selection. We note that this is also the case for prior works, which makes use of similar benchmarks to validate and ablate design decisions. So here they are using not the test set from this, they are using dev set. So test set means it's completely model has not seen, but in dev set you can perform some hyperparameter tuning, right? So there is a little bit of bias, but the paper is saying the previous benchmarks were also doing something like this. We note that this is also the case in prior works, which makes use of similar benchmarks to validate and ablate design decisions. To account for this, we report performance on an additional set of 11 benchmarks, spanning captioning, video, question answering, as well as some less commonly explored capabilities such as visual dialogue, which you saw, multi-choice question answering, etc. The evaluation benchmarks are described in Appendix. We keep all hyperparameters fixed across all benchmarks. Depending on the task, we use 4 few shot prompt templates as described in Appendix. We emphasize that we do not validate any design decisions on these 11 benchmarks and use them solely to estimate unbiased few shot learning performance. All right, so these extra 11 benchmarks are not used for hyperparameter tuning. It's just to estimate the performance. Concretely, estimating few shot learning performance of a model involves prompting it with a set of support examples and evaluating it on a set of queries. For dev benchmarks that are used to validate design decisions as well as to report final performance, we therefore use 4 subsets: validation support, validation query, test support, test query. For other benchmark, we use only the later 2. Other means the remaining 11 benchmarks, they use only test support and test query. Support is the supporting example. Query is whatever question we are asking. We report the results in section 3.1. Section 3.2 gives fine-tuned results for Flamingo, and then ablation studies. So, okay, let's move on to the section. We don't have to read the summary to know what the next section is talking about. Few shot learning on vision language tasks. So first, few shot results. Results are given in table 1. This we already know. Flamingo outperforms by a large margin all previous zero shot or few shot methods on the 16 benchmarks. This is achieved with as few as 4 examples per task, demonstrating practical and efficient adaptation. Okay, this we know. On 6 tasks, Flamingo even outperformed fine-tuned state-of-the-art. This we saw from figure 2. Despite using a single set of model weights and only 32 task-specific examples, as opposed to 1,000 times bigger fine-tuning data set which was used in state-of-the-art fine-tuning. So this we have already discussed in detail at the starting of this paper. Okay, then it is table 2, comparison to state-of-the-art when fine-tuning Flamingo. So when Flamingo is fine-tuned, in how many are we beating the state-of-the-art? Here on VQA V2, on test data set it's beating. Flamingo fine-tuned is beating the state-of-the-art fine-tune. On Coco, it is not beating. On V8 text, which is vision and text, it is beating. Vis, I don't know what data set is this. We can figure it out. I think this is probably some Microsoft data set, perhaps. So in general, we can see that this bold, right? So 32 shot anyway, we are not comparing right now. So 32, it is easy to understand that fine-tuned Flamingo will be, of course, better than 32 shot, few shot prompted Flamingo, of course. For that reason, all these numbers will be bigger than all the numbers in the second row will be, I think, bigger than all the numbers in the first row, which is the case you can see here. Now, third row is the state of the art for fine-tuned models. The other state of the arts existed before Flamingo. And you can see that if you compare between row 2 and row 3, for most data sets, row 2 is in bold color, which means row 2 has a better performance than row 3, right? So this shows that Flamingo fine-tuned model is beating state-of-the-art fine-tuned models in many cases. And Flamingo 32 shot is beating state-of-the-art fine-tuned in 6 tasks out of 16 tasks which they tried. So that is what table 3 is showing. Finally, despite having only used development benchmark for design decisions, our result generalized to other benchmarks also. Scaling with respect to parameters and shots, as shown in figure 2, the larger the model, the better the few shot performance, similar to GPT-3. Obviously, the performance also improves with the number of shots. We further find that largest model better exploits larger number of shots. Interestingly, even though our Flamingo models were trained with sequences limited to only 5 images, they are still able to benefit from 32 images during inference during the multi-shot, few shot prompting. So this table shows the ablation study for different model sizes. So parameter count is 3.2 billion. This looks like comparable models. Yeah, each row should be compared to baseline Flamingo. So in all these cases, it's 3 billion. And for different data sets, what are we comparing? Parameter count versus, okay, these are different parameters. These are ablation studies basically showing what parameters work. We don't have to go through this table 3 in detail unless you plan to implement this from scratch. Now, fine-tuning Flamingo as a pre-trained vision language model. While not the main focus of our work, because fine-tuning is not the focus of this work. The focus of this work is few-shot learning capability. While not the main focus of our work, we verify that when given more data, Flamingo models can be adapted to a task by fine-tuning their weights. In table 2, we explored fine-tuning of our largest model. So table 2 we already looked at. So 3.2 we can fast forward. 3.3 is the ablation studies, importance of training data mixture. We don't have to go through this that much. Then these are the parameters that they are looking at in ablation: training data, optimization. Here actually there is no ablation. It's just I can only see one time step. Then tannist gating, using the tannist gating versus not using. Actually in optimization they are using 2: accumulation, round robin. Then cross attention architecture, they are using gated cross attention and vanilla cross attention. Vanilla cross attention means without tannist gating, right? That's why they are here there is a tick and here there is no tick. Then cross attention frequency in every block versus single in the middle, every fourth, every second. Okay. Okay, so these are the different parameters now they will explain here. So visual conditioning on frozen language model, compute memory versus performance trade-off, vision encoder, freezing language model prevents catastrophic forgetting. Yeah, this catastrophic forgetting is something which I want to show you. Okay, let me show you some more figures from the appendix. Okay, we already looked at this. These are some examples, but catastrophic forgetting they are showing in a very particular figure. Let's see if maybe it's in the main text. Let me just go back up. Yeah, I think it's this one. So this figure in the appendix, figure number 13. This is just showing hallucination. Okay, so here hallucination and ungrounded guesses in open-ended visual question answering. So here there is only one visual, one question. Question: what is on the phone screen? Then answer that is provided is a text message from a friend, but you can't see anything on the phone screen here. So it's a clear hallucination example. Then here question: what can you see out of the window? Out the window. It's some sandwich or something. So it says parking lot, but there is no window. Then question: whom is the person texting? Answer: the driver. You have no idea, right? So here these are examples of hallucination and ungrounded guesses in open-ended VQA. Left part is model occasionally hallucinates by producing answers that seem likely in the given text-only context. Right? If anybody asks what's on the phone screen, yes, in that context of a question, it's a good educated guess, but it's still not correct. But are wrong given the image as the additional input. So here in this, if this image is also present, you can't say that there is something on the phone screen. I can't see anything. Middle similar hallucinations can be provoked by adversarially prompting. So here we are giving an image and deliberately making the model guess something wrong by adversarially prompting the model with an irrelevant question. Then right side, a more common pitfall arises when the model makes ungrounded guesses when the answer cannot be determined based on the input. So ungrounded guesses meaning based on the textual input, image input and textual input, you can't guess the answer. You don't know whom this person is texting. So here image is there, and if image is there, based on the text, you may be tempted to answer something, but if image is there, you know that this answer is wrong. Here image is there, text is deliberately confusing compared to image, and then the answer is wrong. Here from the image and text, you can't assume anything and the answer is wrong, right? So these are some examples where, okay, and then few short examples and more sophisticated prompt design may be used to mitigate these issues. More broadly, addressing these issues is an important research direction towards improving our models applications in open-ended visual dialogue settings. Okay. Now, one more figure I want to show you is this is model, taking video as the input. So these are video frames. There is a question and model outputs the answer. You don't have to, you know what's happening. This is very, very easy. This is a very good example. So look at this. This is a video in which each frame, in none of the frame, the entire word flamingo is there. Only F is there, FL, FLA. So it's like as if you are moving a camera along the text where flamingo is written. And model can understand the full context and answer flamingo. But let's say the model only knew how to look at one individual frame. You can't guess the word flamingo by only looking at any one of these frames. But if you look at the whole frames, it can say it's flamingo. Similarly here, there are three separate objects in different parts of the, on a table or something. And then a video is spanning the table, a pen, a scissors, and some rubber band. So model can answer that. Then what is the object being lifted? So in multiple frames, I think this is a very pixelated image, so I can't also see what's going on. So overall, overall this is good. So overall the actions can be understood and perceived from different frames that are given into the input. Now let's go back to the last page. So we are almost about to wrap up the paper because we are at the 10th page. The main paper itself is only 10 pages, as I mentioned. So we are pretty much there. So one thing we should read here is freezing LM components prevent catastrophic forgetting. We verify that the importance of freezing language model layers at training in row 8. If trained from scratch, we observe a large performance decrease. Interestingly, fine-tuning our pre-trained language model also leads to a drop in performance. This indicates that an instance of catastrophic forgetting. This is amazing, right? Because the language model is forgetting what it had already learned, in which the model progressively forgets its pre-training while training on new objective. In our setting, freezing the language model is a better alternative to training with a pre-trained data set. Now, related work, they are mentioning a lot of related works. This is fine. I just want to read the last discussion section. Limitations. First, our models build on pre-trained LLM language models. As a side effect, directly inherit their weaknesses. For example, language models priors are generally helpful but may play a role in occasional hallucinations. We saw this, and ungrounded guesses. Furthermore, language models generalize poorly to sequences longer than the training sequence length. Training sequence length had only 5 images. In this case, in FewShot, even 32 images were tried. They also suffer from poor sample efficiency during training. Addressing these issues can accelerate the progress in the field. Okay. Second, the classification performance of Flamingo lags behind that of state-of-the-art contrastive models. These models directly optimize for text-image retrieval, of which classification is a special case. Because text-image retrieval is like, for one image, there is only one text or caption. Classification means for multiple images, there is one caption or one class, right? So classification is a special case of text-image retrieval, which means obviously clip model will perform better. In contrast, our models handle a wider range of tasks, such as open-ended ones. A unified approach to achieve the best of both worlds is an important research direction. Third, in context learning has significant advantages over gradient-based few-shot learning methods, but it also suffers from drawbacks depending on the characteristics of the application at the end. We demonstrate the effectiveness of in-context learning when access is limited to only a few dozen examples, meaning 32 examples. In-context learning also enables simple deployment requiring only inference, generally with no hyperparameter tuning needed. However, in-context learning is known to be highly sensitive to various aspects of the demonstrations, and its inference compute cost and absolute performance scale poorly with the number of shots beyond this low data regime. This is fine. Societal impacts. Flamingo offers a number of benefits while carrying some risks. Its ability to rapidly adapt a broad range of tasks have potential. This is fine. Conclusion, we propose, this sentence is not, it's referring to a lot of previous work. Conclusion, we proposed Flamingo, a general purpose family of models that can be applied to image and video tasks with minimal task specific training. We also qualitatively explored interactive abilities of Flamingo, such as chatting with the model, demonstrating flexibility beyond traditional vision benchmarks. Our results suggest that connecting pre-trained large language models with powerful vision models is an important step towards general purpose vision understanding. That's the end of the paper. The appendix section I will skip this time. Although when I started this series, I had an idea that I will not skip even the appendix, but that rule will have to be broken, especially if the paper length is like 54 pages. Right now itself, if I'm not wrong, the total duration of this would be like more around 1.5 hours or more, right? So let's not go through the appendix section. I recommend you to just quickly glance through it, but for major understanding of this paper, just the main paper reading itself, plus going through the figures in the appendix, that will be more than enough. But I hope you enjoyed reading through this Flamingo paper. I definitely enjoyed. Although I'm doing it on a Miro board, I still highly recommend you to take a printed version and then, put your hand and go through it line by line. That's when you understand the model in the best possible way. So thank you so much. We will meet again in another paper dissection lecture video. Take care until then. Bye.